Today we're going to talk about the probability of independent and dependent events. So we're going to start with some vocabulary. Dependent events are multiple events whose probabilities affect each other. For example, if you were drawing two cards out of a deck one at a time, the probability when you draw the first one would be out of 52 total number of cards. But if you don't put it back, the probability for the second card you draw is only out of 51. So those are dependent events. What happens the first time has an effect on the second time. Independent events are multiple events whose probabilities are completely independent of each other. They have no effect on what happens each time. Another type of probability we're going to look at is conditional probability. And for now, I just want you to look at the symbols that we have here. P stands for probability, and we've seen that before. This line represents the words given that. And then the second item in the parentheses is the condition on the first thing in the probability. So this condition limits the probability. When I look at this, I would read the probability of B given that A. And we'll put a more specific example to this in a little bit. Our first example, though, we're going to roll a dice twice. Are the rolls dependent or independent? In other words, when I roll the die the first time and then roll it a second time, will the probabilities affect each other? No. These are independent events. I roll the same die both times. So if I were to calculate the probability of rolling a 1, then a 5, this is how you would write it. The probability of a 1 and 5, and is our key word here. First, the probability of rolling a 1 is 1 out of 6. There are 6 sides on a die, and there's just one 1 on the die. The probability of rolling a 5 is 1 out of 6. There's 1 5 and 6 items. I would multiply. When you multiply fractions, just a quick refresher, just multiply straight across the numerator, straight across the denominator. And I'm going to change this fraction probability into a percent because then it will make more sense to talk about. So 1 divided by 36 is 0.027 repeating, which I will round off to about 2.8%. So the probability of rolling a 1 and then a 5 is only 2.8%. Not great chances. All right, let's change this a little bit. This time we're going to roll a die and then flip a penny. So are the two events dependent or independent? Does what I do the first time affect what happens a second time? No. A die and a penny are completely separate items. What happens when I flip the penny does not affect the die. So I'm going to calculate the probability of rolling a 3 and then flipping a heads on the penny. Probability of a 3 and heads. So the probability of rolling a 3 is 1 out of 6. There's just one side that has 3 on it out of 6 sides altogether. The probability of flipping a heads is 1 out of 2, 1 heads on 2 sides of a coin, and we're going to multiply. So when I have 2 separate events happening, I multiply the probabilities to get the overall probability. Remember, just go straight across the numerator, straight across the denominator. I'm going to divide and change this to a percent so that it can make a little bit more sense. This will be about 8.3%. Again, not great chances of rolling a 3 and then flipping a heads. but better than the other one. We're going to switch to marbles. So in this bag of 10 marbles, this is our total. I'm going to label that just so it's easy to find. I have 3 red, 2 green marbles, and 5 white marbles. You can verify that that adds up to 10 marbles altogether. And we're going to draw 2 marbles out of the bag one at a time. We're going to put the first marble back before drawing a second time. Find the probability of drawing a red and then a white marble. So first I'm going to write out the math symbols. Probability of red, then white. Now, the chances of drawing a red marble, I have 3 chances. There's 3 reds out of 10 marbles altogether. So I draw, see if I get a red marble. I put the first marble back. Now, when I go to draw a second time, the chances I'll get a white marble are 5. I have 5 white marbles out of 10 marbles altogether. The probability then, 3 times 5, 10 times 10. So if I change this to a percent, it's already out of 100. I have a 15% chance of drawing a red marble, putting it back, and then drawing a white marble. Same bag, 10 marbles back in the bag. We're going to draw 2 marbles one at a time again, but this time we're not going to put the first marble back. So we're going to find the probability again of drawing a red, then a white. Probability of drawing a red, then a white marble. All right, so when I go to draw for a red, I have 3 chances out of 10 altogether. Keep in mind, I'm not putting that marble back. I'm going to hold it in my hand. So when I go to draw a second time for a white marble, I have 5 white marbles in the bag, but only 9 total marbles left because I kept out 1 marble. This is a good example of dependent events. When I held on to that marble, it changed the probability of drawing a white marble the second time. I'm still going to multiply. 3 times 5 is 15. 10 times 9 is 90. 90. And I'm going to change this to a percent so it's easy to compare with my first one. 15 divided by 90 is 0.16 repeating. So that is approximately, I'm going to round off to 16.7%. It's a little bit better chance. Not much, but a little bit. We're going to try this one more time. I'm going to put these 2 marbles back in. So I'm starting again with 10 marbles in the bag. This time, I'm going to draw 2 marbles, one at a time, without putting the first marble back. Find the probability of drawing a green and then another green. All right. Let me write this down. Probability of green, then green. Okay, when you do this, first probability is hopefully straightforward. The probability of drawing a green is going to be 2 out of 10. I have 2 chances out of 10 to draw a green. Now I'm not going to put the marble back, so the total number of marbles in the bag now is only 9. I'm going to assume that I drew a green the first time because my probability is drawing a green, then a green. So if I draw 1 green marble, now there's only 1 left in the bag. 2 times 1 is 2, 10 times 9 is 90, And if I change this to a percent, I get approximately 2.2% chance. All right, let's take a look at a few more examples. Something a little more real life. According to a January 2016 report by MarketWatch, 70% of college graduates will leave college with some student debt. It might be more than that now, but for now, that's what we're going to go with. If 4 graduating seniors are chosen randomly and asked if they have student debt, find the probability that all 4 will graduate with debt. All right, let's pick out our important information. 70% have some debt. Okay, 70% have debt. We're going to select 4 graduating seniors randomly. So I've got 4 people. We're going to find the probability that all 4 have debt. So mathematically, I could write the probability that everybody has, 4 seniors have debt. So if I draw the first person, there's 70% chance this person has college debt. Remember, when you're using percents in calculation, you need to change it to a decimal. Draw my second person. There's a 70% chance they also have college debt. The third person, 70% chance they have debt. The fourth person, 70% chance they have debt. And now just multiply it together. If you want to get fancy, this is 0.7 to the 4th power, or you can just multiply it 4 times. The calculator gives me 0.2401, which is about 24% chance that 4 graduating seniors chosen at random have debt. Now we're going to go back to cards. So if you can't remember what all is in a standard deck of cards, because you're not really a card player, that's okay. On our previous notes, I had printed out a picture of all the cards in a deck of 52 cards. This time, we're going to draw 3 cards. Instead of before, we were just choosing like 2 marbles or rolling a dice twice. Now we're going to draw 3 cards, 1 at a time. Key word here is without replacement. So you're going to draw a card and hold on to it, and then you're going to draw another card. So the probability of drawing 3 jacks. Keep in mind, in a deck of cards, there are 4 jacks, and there's a total of 52 cards. So I'm going to find the probability of drawing a jack, then jack, then jack. All without putting the cards back as I draw them. So the first time I draw, I have 4 jacks to choose from out of 52 cards in the deck. I'm going to hold on to that jack that I drew out. The second time I draw, there's only 3 jacks left in the deck and just 51 cards. So assume you drew another jack. The third time I draw, there's only 2 jacks left in the deck out of 50 cards. So each time I draw a card, I'm going down 1 card. Multiply that out on your calculator. 24 over, this is a pretty big number, so calculators are very helpful. And I'm going to change that to a percent, because if someone said you had a 24 out of 132,600 chance of doing this, I would say, I don't know what you mean by that. So if you change it to a percent, do 24 divided by this number, you get 0.00018. Move it over to get a decimal, move it over to get a percent. You have a 0.018% chance of drawing three jacks in a row. Not very good chances. All right, put those 3 cards back, and we're going to find the probability of drawing an ace and a king and a queen in that order without replacement. So each time you draw, you're going to hold on to that card. All right, so we still have a total of 52 cards. Probability of drawing an ace, then a king, then a queen. Keep in mind, in your deck, there are 4 aces, 4 kings, and 4 queens. So the first time I draw for an ace, I have a chance of 4 out of 52 cards in the deck. So I'm going to hold on to that card, assume it's an ace, because I'm trying to find the probability of drawing an ace. The second time I draw, I'm drawing for a king. I have 4 chances of getting a king, because there's 4 kings. But this time out of only 51 cards, because I've held on to my first card. Next, we're going to draw for a queen. So I have 4 chances of getting a queen, because there's 4 queens in the deck. But because I didn't put the first 2 cards back, there's only 50 cards total. When I multiply this together, again, remember, just multiply straight across the numerator and straight across the denominator. And again, change this to a percent so it has a little bit more meaning. And we get approximately 0.048% chance. So a little bit better chance of drawing an ace than a king than a queen than I did of drawing 3 jacks in a row, but still really, really bad odds. Okay, we're going to switch it up one more time and then talk about conditional probability. So put these 3 cards back. So we're back to 52 cards in our deck. We are going to find the probability of drawing 3 clubs, one right after the other, without replacement. So probability of a club, then a club, then a club. There are 4 suits in a deck. There are diamonds, hearts, clubs, and spades. Each suit has 13 cards. So there are 13 clubs in the deck. So the first time I draw for a club, I have 13 chances out of 52. Hold on to that card. We're not replacing it. So now, the second time I draw for a club, there are only 12 clubs left out of 51 total. Hold on to that card. The third time I draw for a club, there's only 11 clubs left out of 50. All right, I'm going to multiply this all up. And then I'm going to divide and change this into a percent. So this comes out to about 1.3%. I encourage you to work this out on your calculator for yourself, just so you can see, verify it for yourself. So the chances are better, 1%-ish chance of drawing 3 clubs in a row, but still not very good chances. So this is how dependent, these are dependent probabilities, and independent probabilities work. The last thing we're going to talk about is conditional probabilities. I have a table here showing the results of a survey of 200 college students, and they were surveyed on the average number of texts that they send each week. So it's split out by men and women, and here are the people who send less than 600. Here are the 600 to 799, 800 to 999, and 1,000 or more texts per week. We're going to find the probability of texting less than 600 given that it's just women. So remember, this line, given that, represents the words given that, and this is the condition. So we're looking at just the women. All right, so if I'm looking at just the women, I need to know how many women total were surveyed, and if you add this up, this is 100 women altogether. So I'm going to find the probability that of these 100 women, they text less than 600 texts a week. Okay, less than 600 is right here. So that would be 61 out of 100. Now this is 61%. So the probability I will randomly select a woman who texts less than 600 times a week is 61%. All right, next one. Try it again. We're going to find the probability that someone sends more than 999 texts, given that it's a man. Okay, given that. Here's my condition. So this represents the total. All right, I'm going to do a little fast math here. 200 people were surveyed, 100 were women, so this better add up to 100 also. So my total is going to be out of 100. More than 999 texts would be this column here, and I'm limited to the men, that'd be 16. And then in percent terms, that's 16%. All right, last example of conditional probability. This is switched around. This time, we're finding the probability that our person is a man, given that they text 600 to 799 times a week. So remember, this is supposed to represent your total amount. So I'm going to go over to my table here. That's this column here. The total number of 600 to 799 texters is 18 and 18, 36. And the men in that group are 18. Change this to a percent and you get 50%. Sometimes I like to think of conditional probability as a fraction, like this line, given that, as the fraction bar, the second item in the parentheses giving me my total, and then the first item being the part out of that total. If you have any questions, you can ask me the next time I see you.